ICAR-CPCRA Regional Station, Kayankulam. Welcome you all to the final day of webinar series, Redefining Agricultural Research and Education Priorities Way Forward, conducted as part of Bharat Ki Azadi Ka Amrit Mahotsav. Today, we are privileged to have an eminent speaker, Dr. Srijit Aravindakshan, econometrician FAO UN. He will be delivering the lecture on data science in agricultural research and education. Dr. Srijit has a research project experience in 4 continents, covering 16 countries of the world. He is the recipient of Erasmus Mundus Joint Master's Scholarship, Dr. Herman Isle Fellowship, Ethic Fellowship, and so on. 4 numbers of master's degree, 2 from India and 2 from abroad. He is the PhD grant holder from Wageningen University and Research, Netherlands. He also has the Advanced Art Programming Certificate from Johns Hopkins University, USA. He is the editorial member of prestigious agricultural research journal, Agricultural Systems. He is a senior fellow of IFSD Australia, and he served as program officer, WWF, consultant economics, CIMMYT, India and Bangladesh. He secured his graduation from Kerala Agricultural University. I welcome you, sir, for your lecture. Welcome, sir.
Thank you, Dr. Nihat. Am I audible?
Yes, sir.
Okay, I'm going to start my, just a second. Can you see my presentation?
Yes, sir.
Okay.
Yes, sir. Visible, sir. Visible. Okay.
Yeah. So before starting my presentation, I would like to thank Dr. S. Kalavadi, head of CPCRI Regional Station, Kayankulam, and also Dr. Nihat Kasturi for giving me this opportunity to present at this webinar series. I also thank the other scientists and staff members of CPCRI Kayankulam for this opportunity. So the world is all about data. So today's presentation, I'm going to talk about data science, but there is a limitation. It's just a pep talk, implying that there won't be too many details, but this is just to motivate the researchers and students to use data science in their agricultural research and in their publications. So that is the purpose of this talk. And so people say that data is a new oil. This phrase, the particular phrase, data is a new oil, was coined by the British mathematician Clive Humby. So do you know why this phrase came up? Because data is so much valuable just like the oil during the 1970s to until recently. So it's so much valuable that people say that data is a new oil. And you might have also heard about these controversies recently in Kerala about the data sharing of COVID-19 treatment and the details of the patients, So there is always this thing going around, even in our state, abroad, everywhere, data is getting more and more importance in our daily life. And every second, we are emitting data. For instance, your mobile phone is sending back and forth enormous chunks of data. Now, let us come back to the topic now. So, what actually is data? Data is a collection of facts such as numbers, words, measurements, observations, and even just description of things is data. Data is a value assigned to a thing. It can be a color, shape, or number, or condition, or size. So we have two kinds of data broadly. One is a qualitative data. Qualitative data is everything that refers to the quality of something. For instance, the color of eye, gender, texture of some object, or your experiences, interviews. And interviews not necessarily, not the surveys that we use to collect data from the farmers. It's not that, but the interviews, the narratives, all this comes under qualitative data. And quantitative data is the data that refers to a number. Example, the number of adopters of a particular agriculture technology, the plot size, the price of farm inputs, for instance, crop yield, etc. These all comes under the category of quantitative data. And the data we can broadly classify into numerical data and categorical data. Numerical data is, of course, numbers made of numbers, and categorical data is made of words. For example, categorical data like eye color, you have a range of eye colors, the gradient of different colors. Then you have gender, male, female, or transgender, blood types, ethnicity, all this comes under categorical data, where you can have the data categorized into different classes or categories. And for numerical data, we have a lot of things comes under numerical data. For instance, the height, weight, or area of land holding. A lot of things comes under the category of numerical data. So numerical data can be classified again into two types: the continuous and the discrete data. And while the categorical data can be classified into ordinal and nominal data. And categorical data is, of course, qualitative in nature, that we have already told, like color of the eye or gender. Numerical or quantitative data is both discrete and continuous. It can be of interval or ratio data also. Interval data has ordered values with some differences, but lack a true zero value. Example, pH. We don't actually have a zero pH, but for a neutral pH, we have 7. And below 7, it's acidic, and above 7, it's alkaline. And ratio data are ordered values with some differences, but has a true zero value. Examples are height, weight. These are examples for ratio data. And we have this categorical data. Then this, as I already said, like, it can be put into different categories. For instance, to explain it more, let us take the example of a condition called used, something used. So if it's a machine or a motorbike or a car, whatever. So when you have the used as a condition, we can categorize, for example, we can have categories for examples like new, used, or broken. So these are examples for categorical data. And for discrete data, these are numerical data that has gaps in between. Example could be like count of vegetable farmers. There can only be whole numbers of farmers. Here for the discrete data, we can't have decimals. We don't have a 0.5 farmer or 0.3 farmer. It's or whole numbers. So discrete data refers to whole numbers. And we have continuous data. Continuous data is numerical data with continuous range. Example, in the case of agriculture, we have crop yield, 2 tons per hectare, 5 tons per hectare, or 0.5 tons per hectare, or whatever, continuous data. So there are all values are possible with no gaps in between them. That's what is implied by the continuous data. Then we have primary data and secondary data. The primary data refers to the first-hand information gathered by the researcher herself or himself. So it's a first-hand information. They go to the field or they do a trial, they collect the data. While the secondary data means data collected by someone else, or it's recorded somewhere, published somewhere else, and you are using that data. When it's not collected by you, it becomes secondary data. So what actually are the steps in data in a study? When we go for a study, what are the things that we do for the study, data collection, and the different processes and steps? So first we have a theory. We have some theory based on which we build up our research. For instance, in social science, when I do research, for example, one of my recently published papers on the agrarian change. So I start up with the theory of conditions for agriculture growth by Bosrup. Bosrup won Nobel Prize in 1965. She published this, and she won Nobel Prize for this great work, conditions for agriculture growth. So there is a hypothesis behind that called Bosrupian, which contrasts the Malthusian theory, which was popular at that time. Malthus said that food production will not be able to meet the demands of a growing population. Bosrup contradicted that, and she said, okay, that's not going to be true. After studying the farmers in South Asia and the population growth here, she said that, okay, all right, Malthusian theory is not going to be right, and there will be technological advancements. For instance, we had this green revolution, and high yielding varieties like semi-dwarf and varieties and high yielding wheat varieties all came. High inputs, use of NPK, and all this contributed to this technology contributed to meeting the demands of the population. So Bosrup said that the technology will be the key, and it will help agriculture overcome the demands of the population, the food and feed demands of the population. So that is one of the theories. So when you have a theory, then you have hypothesis. You have some hypothesis, then you have this research design, how you go with the research design. Then you go for the sampling, then you collect the data, go for the data collection, and you enter the data into some software. For instance, Excel is the most popular software for data entry and management. Then we have data cleaning. In data cleaning, we clean the data. We clean up the outliers, biases, and errors in measurements. We clean all this stuff, and we remove the unwanted or erroneous data from that. Then we store the data. Once we have this data clean, we can store this data in databases, locally on your computers, in cloud. So this is how the up to the data storage process goes, and after that we go for analysis. So before moving into analysis, just we see how we sample the data, which is a critical thing. After we have this theory and we have this hypothesis research design, and after going for data collection, we have to have this sampling. We have to determine how to do the sampling. So sampling, there are two types of sampling procedures. One is the probability sampling, the random sampling. As the picture shows, it's very random. And non-probability sampling is purposive sampling. You purposely cherry pick the samples here. There are caveats for both of these, For example, in the case of probability sampling, we will go for simple random sampling. Simply we go for random sampling, or systematic sampling. Here we go for some criteria we will have for sampling. Then we can also go for cluster sampling or stratified sampling. Stratified sampling, for instance, we will have adopters of an agriculture technology or non-adopters. In the case of non-probability sampling, the researcher will go with his judgment or convenience. So sometimes it's also called convenience sampling. So determining the ideal sample size, we can do it in many ways. One possibility is to do it from your own experience, and you determine the number of samples. But that will not be representative of the population, so it can result in wide confidence interval or measurement error. So another way is to do this, finding the sample size using some formula. One of the formulas is Cochrane's formula. That's given here. Is the desired level of precision that you want to have. And for example, 5% precision, 95% confidence interval. That means you will have only 5% errors. And P is the estimated proportion of the population which has the attribute in question. There will be some attribute in question. So we'll see an example here. For example, suppose we are doing a study on rice farmers of a large village, and we want to find out how many households apply basal dose of granular urea. We don't have much information on the subject to begin with, so we are going to assume that half of the farmers apply basal dose of granular urea. This gives us maximum variability. So the P becomes 0.5. And now let's say that we want 95% confidence interval and at least 5% plus or minus precision. So a 95% of confidence interval level gives us an Z value of 1.96. The 1.96 comes from the table values. There is a table value where already the Z values table which provides the Z values for different levels of precision. I mean, different levels of confidence interval. So in this case, it's very easy to calculate with just normal max. So you get the square of the 1.96, that is multiplied by 0.5 into 0.5 divided by 0.05, the whole square. That will give you a value of 384.16, which is approximately 385. So your sample size in this case would be 385 farmers. This will be enough. It's a statistical way of computing the sample size. And now we have talked about precision, and just in the next slide we can see what is meant by data accuracy and precision. Okay. So actually accuracy refers to how close measurements are to the true value. So in the first bull's eye, you have the data with both accurate and precise, because it's all the arrows are very close to each other and they are on the bull's eye. In the second one, it's accurate but not precise, because all the arrows are not close to each other. That means in your data also, if the measures are not close to each other, if there is wide variation is there between the data points, then the observations, then we say that, okay, it's not precise but accurate. Not accurate but precise, the observations, the measurements are very close to each other, but they are away, they are very much away from the target. So it's not accurate but precise. In the fourth case, it's neither accurate nor precise, because it's all over the place on the bullseye. So this is just to give an idea of what data accuracy and data precision means, and sometimes people use this interchangeably, but there is certainly there is a difference there. And I am coming from social sciences. Although I do a lot of interdisciplinary stuff, I run trials, agronomic trials, irrigation studies and all, but I do come from the social science in agriculture economics and natural resource economics, where we use a lot of regressions, different types of regressions. In regressions, we have two kinds of variables mainly. One is the independent variable. Independent variable is, these are the variables in the study that are under consideration. The cause of an outcome of the study is called independent variable. It's also called predictors. It's also called regressors. And there is another variable is there, it's called dependent variable. The variable being affected by the independent variable. That is the effect of the study. The dependent variable in agronomy, people call, or production ecology or horticulture, or in many fields, they call it a response variable. But economists, they call it dependent variable. This is the effect of the study. So these are used in different kinds of regressions. For example, in ANOVAs, ANCOVAs, MANCOVA, all there, they use this response variable, the name response variable. In regressions, in econometrics, we term it, call it as dependent variable. Just remember that my presentation is not following any order. I'm just giving you some information. This is just to motivate you to pursue data analytics or data science and do it for your research. This is I'm not giving you any comprehensive details, but some information. So here is an example how it is, like the variable in the study, independent variable under consideration, and also the response variable, dependent variable, which is actually what the variable is affected by the independent variable. So we have here a small equation, y is equal to a function of x. So which is the independent variable here and which is the dependent variable? I'll give you the answer. It's like y is the dependent variable and y is affected by x, the independent variable. So that is just a small example here. And we go to the principles of data collection. This is mainly from a social science point of view, I mean from economics that we use in agriculture economics and natural resource economics. So first of all, we need to know what kind of data we need, what type of data we require. So we collect only the relevant data. There is no need to collect a lot of data. In social science or in any other disciplines also, we collect a lot of data. and it is very difficult to manage a lot of variables. And finally, we end up without any productive outcome from that research. So it's very good that we have to have our research objectives very clear without any other changes, and we go with what kind of data we need to collect. We only collect that relevant data. Then we need to have also determine what kind of methods we use for data collection. There are a lot of methods. In social science, we have surveys. In surveys, we use questionnaires. We observe people. Then there are participatory methods. For instance, participatory rural appraisals. Then the participatory farm trials with the farmers. Then we have focus groups where we use a group and we have throw them some ideas, some semi-structured questions. We discuss and we try to collect data. And there is also standard instruments we use. For example, people develop some scoring sheets where they test for this its validity and reliability, and these standard instruments we use. Then there is content analysis. We analyze the content of from the literature or secondary data or somewhere. Then we have experiments, agronomic trials, for example, or varietal experiments. Then we have personal interviews, literature search, meta-analysis, etc. And where, who, and how, and when to collect. That is important. We need to know where is our study area, who should be responsible for the data collection, and how it should be collected, and when do we need to collect that. Along with that, we need to have, we had this slide with theory, hypothesis. Then we had this research design, the sampling procedures, and all. So we need to design our research. Then we go with the sampling procedure. We prepare the fieldwork, schedule a time and for the collection of data. Then we conduct pilots, the preliminary surveys. We assess the situations. Sometimes it will be very difficult, hostile conditions. For instance, I have been to some very remote areas in Mesoamerica. For instance, Brazil and all. Many times people are not willing to collaborate. One thing is that they don't understand English. And I have also encountered a similar situation in India, in Karnataka. I was in Guntur, and I had some hostile farmers. So we have to assess the situation and prepare strategies. For instance, we can have a local contact who can speak their local language, and we use his service. We can inform authorities prior to our mission. So these are some of the things we can take care of during the data collection. So after you collect your data, you enter the data in Excel. Usually, Excel is the most popular data management software. Then you have top row with variable labels in each cell. This is the easy way of managing things. Then we save the entered data as CSV files. CSV file is comma separated variables in Excel, because CSV files are can be easily exported to other softwares for doing further analysis. Excel cannot do modeling, mathematical models. It has very limited capacity, not good for visualizing the data. So a lot of limitations are there for Excel, but Excel is a very good tool for entering the data and managing the data. Once you have your data, you save the data as comma separated values and you store it. And coming to data analysis has been around for a while. For instance, people were starting to analyze the data since 1935, the design of experiments. 39, they had this, the W.E. Deming has this quality control, and a lot of players were there. In 1977 came the exploratory data analysis, which can contain the methods like principal component analysis, factor analysis, and all. And then came business intelligence, followed by machine learning. In 1996, Google Corporation started data analytics. In 1998, there is this two people, the Robert, a gentleman, and Rossi Haka, they developed this R software. I would say R software revolutionized the data analysis, R along with Python. So data analysis became very handy and easily can be used by anybody without a lot of programming knowledge at all. So this is some history. I was just going through some of the history of the data. I will of course share this slide after the presentation. Interested people can have a look at this always. And once you have your data stored and you want to do further analysis on your data, then you have to know your data. So you go for doing a descriptive statistic or summary statistics with mean, median, mode, standard deviation, frequencies, and knowing the standard errors and all. Here you have this different kind of skewness of your data. When you go for the plotting of the distribution, when you have the histograms, you have different kinds of distributions. In the middle, you can see a bell-shaped curve with a normal Gaussian curve. It's called normal distribution. And on the left of the screens, you can see two different kinds of skewness of the data. One is the positively skewed or right skewed, and the other one is the left skewed or negatively skewed. You can easily see how this is. For instance, if you hold your palm and see in which direction the skewness is. Okay, the skewness is on the left, so you have the left skewed data, and you have your right hand, and you just need to check on your plot, on your diagram, on your graph to see the skewness. If you are in confusion, you can use this hand technique and see how the skewness is. And when you write the report or publication, you can mention. So you have different parameters here. For example, you have modes, median, mean, and different those outside. In the case of a normal distribution, those data or data observation that's outside the bell shape is usually we treat them as outliers. I will be coming back to the mean, mode, and median later. So the mean is we can have the population mean as well as sample mean. The only difference in the formula is we have, in one case we have capital N, which is the number of items in the population. And for the sample mean, we will have n as number of items in the sample. So that is the only difference, we have in the case of mean. Mean is also called average, median. So median is the middle value, the value which is in the middle of the observations, a series of observations. So we here have 7. In the first case, we have 7 as the median. In the second case, we have 2 values as medians, 6 and 7. So we will take the average of that, 6 plus 7 divided by 2, 6.5. That is a median in this case. And the mode is the most frequently appearing observation or data in the data set, value in the data set. So here in the first case, we have 11 coming 3 times and 1 coming 4 times. So 1 is the mode here. So it's called unimodal distribution. There are cases also where we have more than 1 mode. For example, in the second case, we have 1 and 11, both appearing 4 times. So it's a bimodal distribution here. These are just examples I give to make the students who are here conceptualize the idea. Actually, I know that researchers here are already they know all these things, but I'm saying this to make the students just to make the concepts clear. Apart from this normal distribution, there are a lot of different distributions are there. So you can see that there are uniform distributions are there. There are Epinechnikov distributions. There are like triangle distribution is there. There are cosine, sine distribution. A lot of different distributions are there. It is just to show that your data may not always have a Gaussian or a normal distribution. So when we fit a model, we have to be clear. We have to be clear about our distribution. Are this particular model we are fitting suitable to our data distribution? If not, how we can make that data normalized to have a normal distribution? There are methods are there. So we can use those methods to normalize our data. We can standardize our data. There are also methods for standardizing our data. Inverse hyperbolic sine transformation, for one example, is inverse hyperbolic sine transformation, which can be used to transform your data to the required distribution. Now let's I'll be just giving you an overview of things, like how we can do R analysis in R. So R is great for doing analysis, and its visualization is great, simply great. So these are all different kinds of plots we can use in R. I had some animations here. I don't know why it's not playing here. Maybe it has something to do with the Zoom screen share. I don't know. So different
I think there is some technical problem with Dr. Srijit sir.
Due to some technical errors, we are not able to continue it right now. Please be here. The speaker will join us soon. The valedictory function of this program will start sharply at 12 noon. Please be connected. Speaker will join soon. The speaker has joined back. He will continue the lecture. Sir, Dr. Srijit, can you hear me?
I'm really sorry. There was some technical glitch. It suddenly went off.
It's okay. Continue.
Yeah, all right. So, can you all see my screen? Hello?
Yes, sir.
Okay. So, R is great. I'll start with where I left. So R is great for visualization. You can use a lot of different graphs. You can create a lot of different graphs and plots and in an innovative way. So these are some of the examples we have here. And for instance, I am trying to visualize my scientific career using data in R. So I have had this R code written here. With the R code, I plotted this graph here. So you can see that here we have 1, 2, 3, 4, 5 different dimensions. One is consulting, publications, research development, and the countries. So all these can be visualized in a single graph. So here, this is not actually possible with a pie chart or with a bar diagram. This is not possible. Here you see that the position of these countries can be seen. How much work I have done with respect to research, development, publications, and consulting. The development, the variable development is indicated by the color, and research is indicated by the size of the bubble, and the relative position of each of these countries in the x-axis corresponds to the number of publications, and for the consulting, it's the y-axis where the respective positions of these particular countries are. So this is one of the examples, with simple R codes and using ggplots, we can have very good graphs. And I made it in the package called ggplot in R, and it's amazing. And let us go on with some basic regression models here. We have, as I said, we have here a linear regression model where y is a dependent variable, x is an independent variable. It's also called explanatory variable or predictor variable. And we have this E random error. Then we have beta 0, the intercept, model intercept. And beta 1 is the slope or coefficient of variable x1 in a linear model. And we'll have a linear model with several independent variables. For example, y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus, like that it goes up to beta n xn plus their atom. So for each of these, we have a coefficient estimate beta, which gives a slope of that particular variable. So these are basics regression, linear regression model, the concept I have explained to you. This can be followed by, again, we have several data points with inputs. Consider agriculture inputs and output yield. So we have a scatter. In this scatter, we have points here, different points marked with respect to the distance from that particular the observation to the input, and the observation is considered as a decision management unit. For instance, it's a farm, and from that we draw perpendicular lines to inputs and outputs. So when we plot, usually we have a linear regression model here. We usually go for the ordinary least square method for that. And we can also have two different models here. I will show you. One is a stochastic frontier model. The other one is a data envelopment analysis model. So if you see here, stochastic frontier, the curve, the production possibility curve here is very smooth. But in the data envelopment analysis, you have piecewise linear frontier. So you have a splitted up lines here. So same data can be used for different modeling applications. That is an example I provided you here. So I use this mathematical programming model using data analysis, and I published 2 papers, both case. So another method that we can use is fuzzy cognitive mapping. Another method, not popular, maybe not popular among agriculture graduates, but it's an useful method when we don't have data that we can measure easily. We can measure the perception or the mental models of farmers or other stakeholders using some questionnaires and some Likert type of scoring sheets. We measure the perception, and we use fuzzy cognitive maps to measure the relationship between cause. Here the cause will be the independent variable, and the effect will be the response variable. So we use the mental models or the concepts or the perceptions these different stakeholders. For example, farmers have on a particular topic or a concept. We can use that, and we can simulate that using fuzzy cognitive mapping, and we can go for analysis. And fuzzy cognitive maps can be easily made using an open access software developed by Wageningen University. It's called Fuzzy Dances. It can be freely downloaded from GitHub. And another method is called choice experiment. Here we analyze the preferences of different stakeholders on different options. For instance, if we give them different kinds of varieties and ask them, okay, which one do you prefer? But it is not like that, and we are going to ask them without giving any details of that particular option or variety. We will provide them with different attributes or the qualities, and qualities of different options will be presented at different levels, and the farmers are presented these attributes in different cards, choice cards, and the choice cards are presented, and they are asked to record their options, and the corresponding attributes and the choices will be further analyzed using different mathematical models. For example, random parameter models or mixed logic models or different kinds of models. And we can use that for publishing and finding results of our data. So here you see a tree of options, different options that we have for undertaking analysis. So this is just an example of how many possibilities are there. But this is not, the analysis is not limited to all these given here, the flow charts, but there are a lot of different options are available. I'm not going to the details of this because I will be providing this as a PDF here. And nowadays people say that, okay, there is no need to go with the statistical significance and p-values. Many people are going with the opinions or propositions. It become propositions in most of the papers. Without a proper model or without any statistical analysis, people go for opinions. And if we go for policies based on that opinions, then it is problematic. So I rely on p-values because p-values offer a first defense line against being fooled by randomness. Sometimes we have a lot of noise in the data, and p-value gives us the first line of defense against those. And bias. There is a difference between bias and error, is there? Bias is actually a systematic error which is caused by the investigator or the subjects, which causes an over or an underestimate of an association. So we have chance or random error. This, of course, it comes from the problems with the sampling error. Then we have bias. We have selection bias. What is a selection bias? Selection bias is sometimes when we go for an adoption study of a technology, then farmers sometimes self-select into the technology. It is not like that the technology is falling randomly on each farmer's household and the farmers are picking it up. Instead, mostly the farmers self-select into a technology. So there is a self-selection bias is there. So we have to go for different methods to correct that self-selection bias. One of the methods is using endogenous switching regressions, Markov chain analysis, and all. Then we have information biases there. For example, misclassification of the differentials. Then we have differential biases are there. For example, there are recall bias. Farmers sometimes say that they have an area of 5 hectares. Sometimes it may not be correct because they say, okay, part of that might have been sold last year, but they still say that they have 5 acres, for example. So these kind of recall biases, people may not recall information with accuracy. So this will lead to erroneous estimates. There are confounding factors are there. It's a situation in which two processes, we are not separating that, and it comes in association. So this is called confounding. Some factors confound the estimates of other factors. Yeah, I already said that there is a statistical noise can be there. Sometimes we interpret things differently. Suppose there is a scatter, and I saw it as perfectly linear here, but my supervisor, he saw it as exponential, and he thinks that it's a new stuff. But when we submit this data in a publication, then the referee will see that it's as a pure noise. So this is how it's always subjective when we use our data, and the data can always be questionable. So we have to come up with bias correction methods and proper models based upon the nature of our data. And now turning back to some of the statistical softwares that are available. There are different softwares are there. The Excel is there. Now if we compare the softwares to cars, then now you can see that R have a strong edge here. So I am an avid R user, and R is one of the most popular softwares, which is open access and can be easily accessed, can be manipulated based on your interest. So if you look at the documents in Scopus and the use of R, you can see a clear edge for R. But we don't, this data is quite old, but now we get a stiffer, our users are getting a stiffer competition from Python. Python is also a very good software which can be used for data analysis. And now I'm going to tell you something, a small bit of information of R. What is R? R is a programming environment. It is object-oriented, similar to S+. It was developed on S+ language. It's a freeware, provides calculations on matrices, excellent graphics capabilities it has got, supported by a large user network. I will come back to that. But let's move on with R. What is R0? R is a statistics software package. No, it's not. It's not like a statistics software package like SAS or Stata. It's not menu driven. You don't have menus like SPSS where you can click and get the estimates or the model. It's not easy to learn. You have to invest some time. It took me almost 6 years of continuous learning to master R. It's not a program with a complex graphical interface. There is no graphical interface in R, but you can use RStudio. RStudio is a graphical user interface that is built by some others for R. But still, it doesn't have a complex interface. You have to code. You have to write codes for running the software. Installing R is very easy. You can have it downloaded from CRAN, a download site, Google it. Then you have base package can be downloaded. Then other contributed packages can be implemented as and when needed. This is the CRAN website. Then you go on with the CRAN site and you download it from there, or can be downloaded. And there are some R tutorials and resource materials are available for learning R. I suggest two books, textbooks. One is The Art of R Programming by Norman Matoff, and the another one is the Handbook by Garrett Grolimond. So these are the two books, one by Matloff and the other one Grolimond. So these are the two books that can be used for learning R. And so these are, we have the R environment. The screen will look like this. When you have this data, the data will be, appearing like that. You can see your data set with the viewing. And I'm going to provide some useful resources, online resources that you can use. That will be very much useful for the students and enthusiasts of data science and data analytics. One is GitHub, where you can store your code and build upon a project. Then you have this Kaggle. Kaggle, you can have a lot of data sets that you can try different modeling. Then you have this Open Science Network, OSF, where you can have a project and you can make your data open source there. You will be provided with the DOI, date of indexing for your data at OSF. You also have the Dataverse project, where you can store your data. And now more and more publishers are going for making the articles, data of the articles that are published to be made mandatory as open access. So that it means you have to have your data stored in some of the Dataverse, and you have to make it available, openly accessible for the public. So I have my for my papers, the data is open access. And when I was working for CIMMYT had this CIMMYT Dataverse, which is linked to the Harvard Dataverse. It's a huge project, and all my research data that I collected are stored in the Dataverse. And whoever wants to do a further analysis on the data set, or just want to replicate the analysis which were done by us, then they can, of course, go for that. Then there is this great site is there, Coursera, where you can learn different data science, machine learning, or programming, different courses offered by different universities. And you will also get credit, and also you will be getting a verified certificate in most cases. If you have questions, if you have doubts on your codes, and if a code is not running properly and you are not getting the desired result, then of course there are forums and resources. For instance, Stack Overflow is where you can ask your R coding questions, and Cross-Validated is another place online where you can ask your doubts on R coding. If you have some errors or bugs in your code, then you can have it validated here. Then you have Flowing Data, which is great for learning data science. Our bloggers are also similar, and these are some of the resources that you can use. And with that, I come to the conclusion of my presentation. And those who wish to contact me for further details, you are all welcome. This is my email ID. Don't expect me to give you a quick answer, because sometimes I'll be very busy, maybe traveling, but still I will try my best to reply and respond to all the emails or questions put forward to me. And talking about me, I also was a student at College of Agriculture, Vellani, 1998 to 2002. I had no idea about doing data analytics. I was a bad student with statistics. I scored very low marks because I had no conceptual clarity on the statistical methods and all. But over the years, when I went to Germany and I learned statistics, I got interest in doing mathematical programming models, various parametric, non-parametric analysis, and that's how I. So a lot of my teachers also helped me. For instance, for getting into getting scholarships, I was helped by my teachers at Vellani. For example, Dr. Anil Kumar, the current dean, Dr. Professor A.K. Sherry, Dr. Professor Pratap, and all these were the people who gave me the reference letters and recommendation letters. They gave me good letters. So always have a good relationship with your teachers. Thank you so much. I'm winding up my talk. Thanks everybody. And yeah, that's all.
Thank you, Dr. Srijit, for sparing your valuable time and views on data science and agricultural research. Of course, data science is the critical factor which decides the quality of our research. Sir, your talk was very informative and gave us an insight towards the data analysis methodology in fixing and redefining future research and education in agricultural science. Thank you, Dr. Srijit, for explaining the hard-to-crack topic in a simplified manner, starting from the very basic level to the most recent advances and free softwares available online, which can be effectively utilized for the future agricultural research. On behalf of the organizing committee, and I express our sincere thanks and gratitude to Dr. Srijit for accepting our invitation